You are the manager of a basketball team. For the upcoming tournament, you want to choose the team with the highest overall score. The score of a team is the sum of scores across all the players of the team, so that's pretty simple. However, the caveat is that you're not allowed to have any conflicts. A conflict exists if a younger player has a strictly higher score than an older player, and a conflict doesn't exist between players of the same age, so it's strictly higher. So given two lists, scores and ages, where each score of I and age of I represents the score and the age of the ith player, return the highest overall scores of all possible basketball teams. So for this example here, why can't we just have a team of all of the players, right? Because that would be 1 plus 2 plus 3 plus 5, which would equal 11. Well, the reason is because player 1 is 8 years old, player 2 is 9 years old, player 3 is 10 years old, and player 1 is 1 years old. The problem is that the player who is 1 years old has a score of 5, which is, as you remember, strictly higher than every other player who is younger than player 4, which means that that is a conflict because they're only 1 year old, which is younger than all of these, and they have a strictly higher score. That is a conflict, which means there's basically two possible teams that we could construct here, right? We could construct a team of players 1 through 3 who have a score of 1 plus 2 plus 3 equals 6, and that would be ages 8, 9, and 10, no conflict. Or we could construct a team of just player 4, who is 1 year old and has a score of 5, which means the better team is to exclude player 4, even though they have the highest score, and just do players 1, 2, and 3. So how do we solve this with brute force? Well, we could just try every possible team. So that's basically every single permutation of score. So we could try a team of just 1. We could try, and we'll label the player numbers. Actually, let's go 1, 2, 3, and 4. We could try a team of just player 1, a team of just 2, a team of just 3, a team of just 4. And then we could try a team of 1 and 2, and a team of 2 and 3, and then a team of 3 and 4, and so on and so forth, right? All the way to trying 1, 2, 3, and 4. Then we could just check to see if that team is valid. So for example, with 3 and 4, we would check, okay, is there anyone else on the team? So is there anyone else on the same team as player 3 who is younger than player 3, but also has a higher score? So we would say, okay, check player 4. Well, player 4 has a score of 5, and he's 1 year old, which is older than player 3, who is 10 years old. So this wouldn't be valid. But we could check, say, this one, and we'd see that player 1 has a score of 1 and is 8 years old. Player 2 has a score of 2 and is 9 years old. So there's no conflict. So we could just check to see if they're all valid. So what would be the runtime of this? Well, first of all, to check every single permutation, if you recall, is going to be 2 to the n, because we'd have to, for every single player, we'd have to check a permutation where they are in there and where they aren't in there. So it's 2 times 2 times 2 times 2, etc., all the way to n. But then we also, for every single player in that permutation, so n, we have to check every other player to make sure they are not a conflict. So that would come out to O to the n squared, which would obviously be ridiculous. So let's try to improve it. So remember, in an interview setting, we don't want to just divine the correct answer. We want to actually think about how we arrive there. So think about one of the bottlenecks in the previous approach, where for every single permutation we find, we have to check every other player to make sure there's no conflict. Is there a way to speed that up? Well, the bottleneck here is having to check all of them, but we only have to see if their age is lower or their age is higher, so lower or higher. That's a sort. So is there a way to sort this in a smart way? What if we were to just sort by age? What if we were to sort the scores by age instead of the score? So the score sorted by age would look like this. It would be 5, 1, 2, and 3. And now, if we were to have a permutation of, let's say, player 1, 2, 3, and 4, and let's line up ages, just to make it clear who is who, and we were to check after player 1, or rather after player 4, we were to check this score, we would see that a score of 1 is lower than 5. But since we've sorted by age, we know for a fact that this player is in fact older than this player. So if the age in this sort goes up, but the score goes down, that is an invalid team. That's a conflict, which means that we can start by just sorting the scores by age, and we should be able to check teams a little more smartly. But exactly how do we do that? Let's consider this much better example for a moment where I've already sorted by the ages. So the score is 2, 7, 4, 5, 12, 9, and 8. And I want you to consider just one of the individuals here. So it's the person with a score of 9. What is the best team that this individual with a score of 9 can be part of? Well, if we look to the right, any person to the right has to have a score of at least 9. And that's because everyone to the right of 9 is older than 9. And if we look to the left, every person has to have a score of under 9. So what is the best team? Can 12 be part of this team? No. Can 5 be part of this team? Yes. So should 5 be part of this team? Well, what we have to do then is consider what is the best team that 5 can be part of. Are you starting to see a pattern here? Well, everything to the right has to be bigger, but let's not worry about that. Let's just worry to the left. Every person who is in the same team as 5 has to be less than 5. So 4 can be part of this team, and 2 can be part of this team, which means that the best team that includes 9, that also includes 5, is the best team that has all numbers less than 5. So in other words, this is recursive. And so you can start to see the solution is going to be dynamic programming. Okay, so this is how we're going to define DP of I, the score of the best team that includes I. And I'm going to run through an example to make it a little bit better. So let's start by looking at 2. 2 is the first number, so we know that the best team that includes this individual, the score of 2, and I'm going to refer to each individual by their score. It's going to be much easier. The best team that includes 2 up to this point is obviously 2. It's the only option. So now we're going to look at 7, and what we're going to do is loop through, and for every individual whose score is less than 7, we're going to find the best team that includes that individual. So 2 is less than 7, so currently DP of here is 2. So now we get to 7, and what happens? Well, obviously we can include 7, so that DP is now going to become 9, 2 plus 7. So now we're going to look at 4, and what we're going to do again is loop through and find the best team that currently exists that is less than 4. So if we look at 2, 2 is less than 4, so we're allowed to include 2, and the best team that includes 2 scores 2, so we're going to include that. Then we're going to look at 7, and we see, okay, 7 is not less than 4, which means we can't include 7, so we're not going to consider that individual, that team. So then we're going to look at 4, and obviously 4 can include itself, which means now we can add 4 to it. So the best team up until now that includes 4 has a total score of 6. So then we're going to look at 5. So let's look at 2. 2 is less than 5, so we can include that. So that means the best team that includes 2 has a score of 2. Then we're going to look at 7. 7 is not less than 2. Then we're going to look at 4. The best team that includes 4 has a total score of 6, which is better than 2, so we're going to change that to 6. And now we can go ahead and include 5, so that score becomes 11. Now we're going to look at 12, and I'll spare you this. We already know that every other individual before 12 is less than 12. So the best team so far that is less than 12 is the team that includes 5. So this becomes 11, and we're going to include the score of 12, so it's going to become 23. Then we're going to look at 9. If we look at 2, that's fine. We can include that. 7 is less than 9, so we can choose that team instead. 4 is less than 9, but their best score is only 6. 5 is less than 9, and their score is 11, so we can change that to 11, but 12 is not less than 9, so we can't consider that team. So the best team that includes 9, so we're going to include 9, is a score of 20. Then we're going to look at 8. 2 is less than 8, so we can include that. So it's 2. 7 is less than 8, so instead we can consider the team who includes 7, so that's 9. 4 is less than 8, but the team that includes 4, their score is only 6, so we don't care about that. 5 is less than 8, and the team that includes 5, their score is 11, so we'll change that to 11. 12 is not less than 8. 9 is not less than 8. So that means we can add 8 to this, and that becomes 19. So the team that includes 8, their score is 19. So then what's our solution? The team that includes 12, the best score that you can create with a team that includes 12 is 23. So we return 23. So what is the runtime of this? Well, we first have to sort it, so that's n log n. Then we have to do our DP run. So we have to consider every individual, and then for every individual, we have to consider every other starting team. So that's going to be an O of n. So the answer is n log n plus n squared. So that's just going to be O of n squared. So the first thing we need to do is sort by ages. So the best way to do that is just to create a vector of like age score pairs. So that's what I'll call it, age score pairs. And then let's also create our DP vector. So DP, and how large is that going to be? Well, that's just going to be the number of individuals, and they're all going to start with a score of 0. We need to have a integer that we're going to return. So let's go ahead and do the sort. So what I'll do is for int I equals 0, I is less than scores.size, I plus plus. We'll populate that pair vector. So that's going to be age score pairs. Push back, and we'll make a pair. And the pairs will be their ages, because we first want to score, ages. We want to sort by the ages, and then we want to do break ties by the scores, right? So then let's go ahead and sort that. And since in C++, it'll automatically do the sorting first by the first member of the pair and then by the second member. So we don't have to create any custom sort functions or anything. Okay. So now let's go ahead and do the DP. So just run through every number for I equals 0, I is less than scores.size, I plus plus. And then for every individual, we need to consider every other individual before, because we need to find the best team that includes that individual from that point. So for int j equals 0, well, j is less than I, j plus plus. And what do we need to check? Well, we need to check if age score pair dot of j dot second is less than or equal to age score pair of I dot second. So that's if this person has a score that is less than or equal to the individual we're considering. So if this team is already better than the best team that we've found, so dp of j is greater than dp of I, then we're going to change the dp to this. So dp of j. Okay, so after we finish considering an individual, so we've looped through I, then we need to go ahead and add this individual's score to the DP, because we're going to include this person in the team. And then we want to check to see if we found a new best solution. Just like that. And that should actually be it. So let's go ahead and try that. First try? First try. All right. So thank you so much for watching.